before we start, is there anybody who wants to take notes this class? Anybody who hasn't yet taken notes for 3% bonus in the grade? Anybody left? We'll have to think about what to do. Nobody here today? Right, well, we'll have to think about what to do in terms of compensating if people want to retake it. We'll think about it. Maybe we might. Right, maybe we'll do it a public auction style. Anybody willing to do it for less? Just kidding. We'll think of something. This one will be okay. I have notes that I have notes, my own notes and lists for this lecture, so it'll be okay. Also, before we start, and so that I don't forget, so on Thursday we have a conference here, the Gatsby conference, so there won't be class. You're all invited to come to the lectures throughout the whole conference. I'll send something into the Moodle also. I'll try to maybe, if I have time, highlight specific lectures that might be relevant to things we've seen.
The conference is only on Thursday?
It's Tuesday through Thursday. Yeah. I'll send the whole program for the conference to you guys so you can see. Okay. So let's get back to where we were a week ago. It's been a long time. We're studying the same structure of equations and dynamics that we've been looking at basically all throughout, and very similar to the Hopf field, but the Jij matrix that we're using is now totally random Gaussian independent. Every Ij is totally taken independently. We've shattered the symmetry that we previously had in the Jij matrix. And so that's the equations that we're studying. We used the results of Gurko's circular law in random matrix theory, which told us about the eigenvalues of this kind of random matrix, that they're distributed throughout this circle in the complex plane, with the maximum point basically being at G. The radius of the circle is G, which is our parameter here. And so we found from that the simple zero fixed point breaks when beta times G is greater than 1. Right? That's when we found the effective dynamics of this whole system. There was a positive eigenvalue of those dynamics. Stability of zero fixed point breaks when beta G is greater than 1.
Right, it breaks the probability, right? It doesn't necessarily break.
So that's technically true because this is a probability distribution on the eigenvalues. It turns out that in the large n limit, this is really the distribution of the eigenvalues for the matrix, and so with probability 1, it will break. It's true that for any finite n, if you're right at that critical point, it may or may not break. There might be some kind of little fudge over. It might have to be greater than 1 plus some small epsilon or something like that. But anything notably larger than 1, it'll break 100%. Okay. Now, just to rescale things and make our lives easier in a little bit, I'm going to basically bring the beta inside the matrix. So notice that beta Jij is also Gaussian. We're just kind of multiplying a Gaussian by a constant. So it's got a distribution. Its mean is still 0. And instead of the variance being G squared over n, it's beta G squared over n. So that's just an observation. And now to make our lives simpler for the sake of notation, we'll define a parameter J, which is just beta G. So I'm just kind of swooping the beta parameter into our matrix parameter because they're effectively going to come together. And now we're going to have a Jij matrix that's distributed 0 with this j squared parameter over n, and our dynamics are just going to be si dot is minus si plus tangent h sum over j, jij, sj. So just to make our lives easier, there's no beta, but it's still there. We just have two different parameters that effectively their effect is a combined effect where the product is the only thing that matters. So we can treat that as one single parameter. Okay. Now, okay. Now now hi, the sum over jij sj. That's going to be our input into neuron I, as it's always been. Now, as we observed when we were studying the Hopfield network, we looked at the sum over jij sj, and we wound up saying that was a Gaussian. That was going to wind up being in the large n limit, a Gaussian. And we're basically going to study the statistics of that hi. That's effectively what we're going to do in order to study the chaotic system as well. So
we find the two different matrices with the same letter J. Why both the same matrix?
This
This and the upper one.
So we're gonna forget the upper one.
Ah, okay.
We're going to define a new jij, which has absorbed beta into it. Thanks for clarifying that. And that's the matrix that we're now going to study from now on. So we just absorb the beta parameter into our definition of the matrix. Okay, and we want to study the statistics of the input onto our neurons, which is basically what we did in Hopfield. We studied the fixed points, and we studied the statistics of hi, given, for example, that all of the s's were aligned with a given one of the memory patterns, with the first memory patterns, for example. We put in an sj that was equal to the memory patterns, and we calculated hi statistically. We said the expected value of it is going to be aligned with the correct memory pattern, and then it's going to have some variance. The overall statistics of it will be Gaussian. So we're going to do the same thing, the same kind of thing here. Now, the key additional thing that we're going to have here is that we're going to make the argument that sj is independent of jij. Okay. So why can I make that? Why am I making that argument? So sj itself, that's the activity of the Jth neuron. That depends on elements of the matrix of the form jj k for all k. Right? Now, up until now, we had symmetric matrices where one of these elements was exactly equal to jij. So we had some element of the matrix that was going to form a loop. If jij was large in Hopfield, for example, or when we looked at the symmetric matrix, if jij, for example, happened to be large, it meant that jji was also large. So that sj and si, the two neurons, kind of would be mutually reinforcing each other. And then we couldn't properly assume that sj was independent of jij. Because if jij was large, then it meant that si was also going to be driving. Not only is sj going to be driving strongly its input into neuron I, but also the reciprocal connection was also strong. So neuron I would necessarily be strongly driving sj, and maybe they wouldn't be independent. But now that we've broken that symmetry, we have no reason to assume that there'll be any kind of interaction, a substantial interaction. In particular, right, all of these jks, by definition, are independent of jij.
So it was a bit little fast.
Yeah. So, and it's also a little bit gently hand wavy. But the argument is essentially that, right, Fj depends on the row of the matrix where we have the input onto neuron J is coming from the jth row of our matrix, J, J, K, for all K. And all of these elements times the network activity at any given time, those are going to determine the input into neuron J, right? But by definition, all of these elements of the matrix have been chosen totally independently of all the other elements. In particular, if we're looking at some other neuron I, and we're looking at Jij, it's been chosen totally independently from the same Gaussian distribution. So the input that neuron J sees could be large, could be small at some point, or if there was a fixed point, at the fixed point it could be a large input, or it could be a small input, and it'll be totally independent of what Jij is. Right? The way that and Jij is the way that neuron J is going to affect neuron I. And that's going to be a key argument for a lot of our calculations. And with that argument, we'll go on to study the statistics. Effectively, we'll go on to study the statistics of HI. Okay, so that's like I tried to motivate before. That's effectively what we did in a lot of our study of Hopfield, was to notice that HI, effectively, as far as we're concerned, has a randomness due to the Jij, and then study its statistics. Now, in the chaotic dynamics, we have things that are also changing in time. So when we studied Hopfield, we were interested primarily in fixed points. We assumed a state that was not changing in time, and then studied the statistics of that state. But now we'll be interested also in statistics that change in time. So we'll have statistics that include the time average value. We'll denote it with this angle bracket, time average HI. And then we'll also have a population average. And it'll be important to keep both of those in mind, so that population average will be denoted by a square bracket. And every time we look at an average, we're also going to be interested in the fluctuations or the variability around that average. So the fluctuations in time so if we look at a single neuron input HI, we'll be interested in the variance over time of that input, right, which is just equal to the mean squared minus the square mean minus the mean squared, right? The variance of its input in time. If the whole network is at a fixed point, so then this will be zero. Nothing changes in time. Everything's fixed. If there's some kind of chaotic dynamics, then we expect this to be non-zero, at least in the population average. So we'll look at the population average of this term, average over all neurons of their temporal fluctuations, right? And we've got to be careful about the order of all these averages, because there's other averages we might be interested in. We might be interested in looking at the time average of single neurons and how they differ one from the other. So that would be the variance of this time average. Yeah, so this here is a temporal fluctuation, right? So the square is inside the time average. So this is a variance over time. And then we can calculate that for a single neuron, and then we can take the average of that over all neurons. Delta is the difference of HI from its mean. We can take that as a definition. It's the this is a variance.
Okay.
Yeah, this is a variance. I'm just writing out explicitly because we have different things that we're averaging. We can average over time and we can average over the population. So we have different variances. So if I just said variance HI, it's not clear what I mean.
But correct. So the second law is not the variance of the population, it's the expected value of the temporal variance, right?
Yeah. Right.
Because you,
You get the fluctuation in time over of the whole population.
Yeah. The average fluctuations over the population. But I might also be interested in looking at a single neuron's time average and how this varies the variability over the population. So there's a fluctuation in time, but I might also be interested in variability in space, as it were, variability over the population. And then I should put the delta outside of the time average. And also put the square, when I formally write what that means, put the square outside of the time average. So I first take the time average. Every neuron might have a different time average, or they might all wind up having the same time average, and then take the average over the population. Okay? So these are two different forms of variances of variability. One is a fluctuation of variability in time that I'm afterwards averaging over the whole population. And the other one is a variability in space, a variability over the population, where first I take a time average. And those are two different statistics that we might be interested in. With this one? The difference between the two of them.
Yeah.
Right, so here we first average over time. So maybe the arrows are confusing. So here I'm looking at the statistics of a single neuron, and its input might be varying in time. And I calculate that variance over time for a single neuron. And then only afterwards I say, okay, every neuron maybe had a different variance. Maybe some neurons were totally fixed in time, and other neurons were fluctuating wildly. So I say, what's the average variance over the population? In the second one, I say, well, let's basically ignore the fact that every neuron is fluctuating, but let's just look at its average over time. And then look at the variance of that. See, the time average of the single neurons are identical or different. And that will be the extent of the variability. So if the spatial variability is 0, then all neurons' time average, it means that all neurons' time average is the same value.
all right. So in the last term, after you take the expected value with respect to time, then you get a number, not a random variable. Or is it a random variable?
So
what are you averaging?
It's a good question. Well, I'll take the average over time, but I still have a whole population, right? So I'm still averaging now. I can still ask about taking an average over the whole population. It's a good question in terms of the randomness. Kind of what's the source? The source of the randomness is still really the matrix Jij. And it turns out, this is a subtle point, but it turns out that similarly to what I mentioned when it comes to eigenvalues, it turns out that these kinds of statistics, it'll be identical to say what is the average over different instantiations of Jij. If I look at a single neuron but build a new matrix every single time, that will be effectively identical to doing a population average or a population variance. But in terms of the statistics of the system, what I really mean, what I'm interested in, is if I look at the whole population. So I have a time average for every neuron, and then I can just look kind of like, think about it like an empirical average and empirical variance over the whole population. And that's what I mean here. I'm looking at the whole population, and I'm setting the variance across the population.
So because it is like in the large n limit, it's actually another distribution of the, like for spinal.
Well, I can think about that kind of empirical average for any system. I might have 3 neurons, and I say, what's the variance over the 3 different neurons, right? In terms of kind of the subtle point, is that effectively it turns out to be identical to doing a variance over building new matrices every time, doing a random new instantiation of the matrix. But that's definitely a more subtle point that is beyond the scope of our class to really justify. Okay, so this is to get us into the mind of the different kinds of averages and the different kinds of variability that we are going to be faced with in studying the system. Now I want to talk about the scaling. So something I mentioned when we presented this model is that when we have a Jij of this form with the variance scaled as 1 over n, it means that the typical size of a synapse, or the typical absolute value of a synapse, is like 1 over square root of n. So now I want to kind of get into that question of scaling a little bit more closely and carefully. Okay, so here we have a single Jij. Absolute value is typically going to be order 1 over square root of n. And now the typical value is going to be order 1 over square root of n. So now I'm going to kind of want to probe why that's important and how that makes sense. Because we noticed that and I said that's kind of different from models that we've seen in the past. When we saw the ring model, for example, we had a scaling there. Each Jij was scaled with 1 over n. And people asked, why is that the right scaling? And Neuroscience said, that's the scaling that makes sense, because effectively the net input onto any given neuron in the network in that scaling is going to be independent of the size of n. We study the system, and the kind of mean dynamics, the dynamics of single neurons winds up being independent of n in that scaling. So I want to see what happens if we try to impose kind of that, what would maybe seem like the more obvious scaling. So I'm going to introduce an alternative network with a conventional scaling. And for the physicists, this might also be called a mean field scaling sometimes. So I'm going to define a different matrix, Jij, just equal to some parameter j tilde, and this time each Jij is either going to be plus or minus j tilde divided by n. So this might be the scaling that we would think is appropriate to have kind of net dynamics that be independent of the size of the system. I'm assuming just with probability 1/2. Okay, so the average Jij is going to be 0, and what's the variance of Jij? What's the expected value of Jij squared? J tilde squared over n squared, right? Every Jij has value Jij value squared equal to j tilde squared over n squared. So we see now why this is a fundamentally different choice than we're making in our chaotic network. The variance here in this case scales as 1 over n squared. Okay. Now let's see what happens to our hi, input into neuron I. So we have sum over j, Jij, that's j. And now, just kind of for the sake of gathering more intuition about these systems, I'm going to separate the sum into those Jij's that are positive and those Jij's that are negative, right? Approximately half of them are positive, approximately half of them are negative. So I'll separate those out. The sum over Jij's that are positive, Jij, Sj. I'm going to think about that as the excitatory input, kind of in quotes, to neuron I, and then separate out Jij less than 0, Jij, Sj. Call that the inhibitory input onto neuron I. Now, why do I say that it's in quotes? Why do I say it's quote unquote the excitatory and inhibitory input onto the neuron? Right. In our model so far, we haven't bothered to make sure that Sj is positive. We could change from tangent hyperbolic to something else and make sure Sj was positive. We could do that, but for now, Sj might be negative. Another important reason, though, is the structure of the Jij matrix, right? In a biological connectivity matrix, any single Jij that's negative, the entire column, right, meaning the entire set of outputs of that neuron are all negative. A neuron is either inhibitory in all the synapses that it sends or excitatory in all its synapses. That's almost entirely, almost as a law of nature, not exactly, but right. In our matrix, that's not necessarily true. The same neuron in an output to one neuron, in a synapse to one neuron might be positive, in a synapse to another it might be negative. We'll get to networks. We'll get back to networks that have the biological realism, and it turns out a lot of things will be fairly similar to this case. But so for now, it's in quotes excitatory and inhibitory input. But nevertheless, let's study those. So what's the time average of the excitatory input to neuron I? So just looking at the first part of the sum and take the time average here. When I take a time average, the Jij's are fixed, and I just take the time average over the S's, right? So I have sum over Jij's, which happen to be positive, Jij, time average Sj. Okay. Now each of these Jij's, the ones of them that are positive, they're all just equal to J tilde over N. So I can take that out of the sum, and I have J tilde 1 over N sum over the Jij's, which happen to be positive, Sj. Okay. Now, how many elements in the sum do we have? We have very close to half. Not exactly a half, but very close to half. And now, a key assumption I made is that, like I said before, that Sj is independent of Jij. In this case, it means that Sj is independent of whether or not the Jij is positive or negative. Right? The neuron J doesn't care whether its output to a given neuron happens to be positive or happens to be negative with regard to its own activity. So I can assume, because of the independence, I assume that this whole sum is just summing over approximately half of the network and taking the time average. So this is very close to, I have the J tilde, 1/2, and it's very close to just the population average. Population average over the time average of the neurons. And we'll come back to how close it is to that population average. But effectively, the net input, this is, I think, similar to things we've seen before. We're summing over a large number of neurons. In this case, we took about half of them. And so effectively, the net input just depends on the population average. The neurons effectively summing over the whole network. And in this case, we're looking at half of the input. So it comes out to J tilde half of the population activity. And similarly, if we look at the inhibitory, quote unquote inhibitory input, then we'll pull out a negative J tilde, and we'll have approximately negative J tilde and times a half of the population average timed average, I think. This is in the end, after I've already taken, the 1 over n goes into the population average. Population average is 1 over n, sum over all the neurons.
Here you use the assumption that the independence is
Yeah. Okay, and so these results can make sense. So the net input, I call it excitatory and inhibitory inputs, they wind up being independent of n. This is the kind of scaling argument that justified why in the ring model we took this kind of scaling, where each synapse had the size of 1 over n. So that the net input to a given neuron was order 1, was independent of how large I took the network. Okay, so that's all well and good. We'll notice that this suggests, though, that the time average net input to HI, to a given neuron, is going to be approximately 0. The quote-unquote excitatory part is exactly negative from the inhibitory part, so it'll be approximately 0. And now, so let's hold off on what it means. We'll come back to it. And so this is approximately 0, and these are approximately j tilde times half the population average. Now, if I look at the population, average here, I just did the time average onto a single neuron. Now let's look at the population average of the time average. Let's look first at the excitatory input. So now I'm taking a population average, not just a time average. So I have sum over the jij's that are positive for a given I, jij, and then the time average of j. Now again, I'm going to apply that assumption that Sj is independent of jij. If Sj is independent of jij, then when I take the population average, the average of the product is the product of the averages. So in that case, we can write this jij and Sj. Okay, so again, I used the assumption and the argument that Sj is independent of jij. Again, what it means in this network is jij, neuron j's synapse onto neuron I, whether it's positive or negative, is totally independent of j's activity. Neuron j doesn't care if it's positive or negative. Now, that assumption would be different, for example, if we actually separated neurons into, here's a whole bunch of them that are excitatory, and here's a whole bunch of them that are inhibitory. And then those two populations might have very different activities. So then we couldn't quite pull this apart so easily, because then we would say, okay, if the excitatory neurons activity is higher, then there's a dependence between whether this synapse jij is positive or negative and the activity of neuron j. But in this case, the population's all mixed. There's no dependence between the sign of jij and Sj's activity. Okay, so we can pull out the product, the expectation of the product into the product of the expectation. Okay, and now when we have an average, it becomes this approximate value becomes exact. So this just becomes exactly j over 2, population and time average. I should be a little bit more careful here. Really, this is kind of a nonsensical. I don't really want to be more careful, but to anticipate well-justified questions, it kind of doesn't make much sense to take the average of jij and then have a sum over whether jij is positive or not. So I sort of have to keep the average of that whole sum, the average over over the sum of whether Jij's are positive. Kind of, I'm averaging over how many Jij's, how many of the inputs to a neuron are positive and how many are negative. On the average, it's half. It's exactly half, right? A single neuron might have a little bit more than half or might have a little bit less than half, but the population average is exactly half of the synapses are positive. And so we get J tilde over 2 times the population activity. And identically, when we calculate the inhibitory input, we'll get exactly negative J tilde over 2 S. And the net input averaged over all neurons will just be 0. Yeah.
If you're taking the average of the population of some, shouldn't it be already 0?
No, it's the sum of just the Jij's that are positive. So that's still in my definition. That's why it's 0 in the end. Yeah. In the end, the whole thing. That's even simpler. I could have directly jumped to this and said it's 0 just by looking at this definition, and then I wouldn't have had any of the ambiguity of what I average. If I just look at this and take the expected value over the population, it'll be 0 for sure.
I'm not sure, but maybe the sum over the average of Sj, shouldn't it have like n squared divided by 2 terms rather than n divided by 2 terms?
No, I'm looking for this is for a single I.
Okay.
Summing over J for a single I. Okay, so that's the population. That's the average over the population. Now, what about the variability? What about the What about the population variance or the variability? I've kind of already said that every neuron will be close to the average, but so I'm kind of being a little bit pedantic and going through the full calculation of it to show you how close every neuron's time average will be to the population average, right? So what we're going to calculate is the variability across the population, the variance, what I call the spatial variance. So the spatial average is 0, and now we want to calculate the spatial variability after time averaging. So we want to calculate time average of HI squared, averaged over the whole population. Okay, now I'm going to be pedantic and kind of grind out the calculation a little bit. We could sort of right away argue that this is a variance of a sum, the variance of a sum Jij, Sj, and just say a variance of a sum for independent random variables is the sum of the variances. But I'll work it out explicitly, and then we'll go back to that statement. So, writing out explicitly the value of HI time average squared. So, sum over J, Jij, Sj squared, and if it's squared, I can just write it again. And just to make sure that we're going to be careful about indexes, this time sum over k, Jik, Sk. But this whole term is identical to this whole term. So this is the square of HI, time average. Now when I take this product, I should be careful about terms. I have n terms in which j is equal to k. And then I have n times n minus 1 terms in which j is not equal to k, right? The product of a sum of n terms times n terms is n squared terms. And within those terms, we have n of those that are exactly identical. So for those, we just write Jij squared, Sj squared. Then we have another n times n minus 1 terms coming from this product, where j does not equal k. Jij, Jik, Sj, Sk. Okay. Now we have these sums, so let's bring the expectation value, the average, inside those sums. And also, again, apply our argument that Sj is independent of Jij. So we have sum over J, the average, population average of Jij squared, population average of Sj squared, plus sum over J not equals to K, population average of Jij times Jik. Now I also know that Jij and Jik are independent, so I can write the expectation of their product, like the product of their expectations, times this Sj Sk term. Okay. What happens to this term? This term we have to be very wary about because there's a lot of elements in this term, right? There's n times n minus 1 elements. But this average is 0, right? So this whole term in the population average is going to give 0. And that's the point where we're using the independence of the different elements of the sum, right? If we, to begin with, just said, which we could have said, like I said, we could have just said the variance of the sum of independent random variables is the sum of the variances, then we would have immediately jumped to this line. And we would have effectively been saying, okay, we know that this part is going to be 0 by the independence. But just to work it all out, so we have the sum over n elements times the square means, which is, so we have, sorry to write it down here, but we have n times the average of Jij squared is J tilde squared over n squared times the, no, just a dot. Times whatever this is. For now we're saying we don't know what the population activity is, but there's some mean squared of the population activity. So we have n times something over n squared. The whole thing is order 1 over n. Okay, so what does that tell us? We looked at the variability, the variance over the population. We find that the variance over the population is very small and shrinks with n. It's 1 over n. So effectively, every neuron's time average is identical, right? So here, when we said that it's approximate up to some deviation, which is effectively order 1 over square root of n. So it just kind of justifies what we said about the approximate values of input to individual neurons. Okay. Okay, let's keep powering through and look at the temporal fluctuations. So somebody asked before, what does this mean? So the net input onto a single neuron averaged over time is 0. So that kind of seems like maybe that's not very interesting. Every single neuron time average is over 0, but maybe there's something interesting that can happen in the fluctuation. So let's look at temporal fluctuations. Again, that means that we need the h squared inside the time average. Let's study the variance of the over time for a given neuron. Again, we'll have a term that looks very much just like this. They're taking the product of n terms. So I'll jump ahead and write it in the 2 parts. One part that comes from the term where j equals k, that has jij squared, sj squared, where now, again, we're just averaging outside, squaring inside the average. And then we have sum over j not equal to k, jij, jik, sjsk. So that's the fluctuations of a single neuron's input over time. I'm wondering to go through the argument. We can argue also that this itself is already small even before we take the population average, but I'll skip that. I'll skip that argument and I'll say, okay, well, we're interested in the whole population as a whole. So let's look at the fluctuations of a single neuron and average that over the whole population. Okay, so then we're just applying population averages to what we have here. And it looks almost identical to what we did here. Again, sorry for being very pedantic and kind of going through things very slowly, but again, what we'll have from the second term, where j not equals k, is in the population average, jij and jik are independent, and they both have mean 0. So the whole term goes to 0. And again, we're left with a situation where, now the variability in time, the fluctuations in time, have a variance which is made up of n terms that are, each one of them, 1 over n squared, times something that's order 1, we don't know what it is. So the whole thing is 1 over n. Okay, so after that very careful working out of different averages, different variances, we thought that this scaling might make sense because the 1 over n will give us this kind of maybe excitatory input that's order 1 and inhibitory input that's order 1. But we find effectively that all the neurons have time average input that's 0, and not only that, but the fluctuations from the time average are very, very small, 1 over n. So effectively what we found is in this network, everything's just 0, up to some very, very small, potentially 1 over square root of n terms. And the parts that may be of interest to us, these parts that are maybe fluctuating, that have a variances, those are dependent on population size. So the scaling gives us something where in the mean we have something that doesn't depend on population size, but in the variances we have something that shrinks the larger and larger population is. Okay? And that gives us motivation for the scaling that we do see, that we did use, that we will use in studying the chaotic network. Okay, so we see that we kind of need stronger interactions between the neurons for essentially interesting dynamics to emerge, and we'll get to that in the second hour. כן. כאילו הייתי... תראי, זה קרוב לאפס, אבל אני לא בהכרח יודע איך זה מתפלג, קודם כל. כלומר... אבל מכאן הייתי יכול ישר להכניס את ה-population average. נכון. כן, יש שאלה אם זה ממש אפס או מה יהיה הסקיילינג של ה-1 חלקי שורש n, ואם אני רוצה לדייק, אבל צודקת, במקום הייתי יכול... נכון. כן. לא, זה נכון. כן. זה נכון, בכל זה אני כאילו חוזר על דברים שכאילו עושה ניסוע הרבה פעמים שלא לצורך, קצת לתרגל את הניסוע הזה והניסוע הזה, ופה רציתי, כן, אני חושב.
יש לנו איזשהו ביטוי, כאילו בשאלה הראשונה, ואז אנחנו בעצם שני ביטויים, שכאילו אחד מזה זה המדינה ואחד מזה הרעש. אנחנו כאילו מתייחסים לשניהם בתור משהו גאוסיאני ואנחנו בלתי גאוסיאני. עכשיו, בחיבור של הגאוסיאנים האלה, אנחנו באמת יכולים להגיד שניהם דברים להם בלתי תלויים. כלומר, זה נראה כאילו לכל תרם מטריצה יש לנו איזשהו משהו שיכול להיות 0 כפול 0 כפול 1 כפול 2, אבל זה בדיוק שחוזר גם פה וגם פה.
כן, גם אלפא צריך להיות זה לחבר את הווריאנס.
אז כאילו הצד הבא,
הסיבה שכן זה בעצם כי האלפא IJ הזה עובר דרך דברים שהם בלתי תלויים. אלא אני כופל את זה כפול קודם כל אני סוכם כולן אני כופל את זה כפול משהו שהוא בלתי תלוי.
זה מספיק בשביל להגיד, כאילו, כלומר, עצם העובדה שהפקטור הזה הוא אותו פקטור, יש כמה איברים שבהם זה בדיוק אותו פקטור, כאילו.
כן.
גם נורא רוצה להיות מעבדה, אבל צריך את לחשוב על משהו.
כן, זה שאני מכפיל את זה במשהו כל פעם בלתי תלוי, בממצא 0. זה חשוב לך, אבל זה...
כאילו, הצעדים הבאים זה גם די קל, כאילו, יאללה בשביל אוטופיה, אבל אולי ניקח אזור יותר גדול.
אבל אז זה כן קובע את
כן, אבל מה אתה קובע בעצם? כל פעם יש חלק של 0, יש חלק של 1, יש חלק של 2?
כן.
נראה לי נהיית שם.
אבל
אני ראיתי את זה
כאילו אתם יכולים לחשב ליתר ביטחון את הקובעים, אבל זה כן, כאילו בעצם זה ממוצע 1 וזה ממוצע 0.
זה לא גם למה זה כשלעצמו אומר...
לא, ואז תראו ביחד, זה ממוצע 0 וזה ממוצע 0 וזה ממוצע 1, והכפל, ואז הממוצע של ה... כן, האי של האקספקטיישן של הכפל.
אבל יש להם את של האקספקטיישן של זה כפול זה שזאת בפגישה של וריאנס, יש חלק של מכפלת המקרים.
נכון, אז זה מה שאני אומר, בעצם הייתם יכולים לבדוק ליתר ביטחון, להכניס ולראות מה...
אבל האינטואיציה כאילו יותר...
אז ברמת האינטואיציה זה שפה יש איזשהו J.I.J שהוא בלתי תלוי לגמרי מאלפא J.
אנחנו אומרים כי אנחנו מאבדים יציבות עבור בטא G שגדול מאחד, ואז
אני צריך לחשוב טיפה כאילו כמה זה מצריך את העניין שזה גם J.I.J שהוא ממוצע 0.
מאבדים יציבות או קיימת יציבות?
או לא, אבל...
אם בטא G גדול מאחד, אז מאבדים יציבות.
אבל ברגע שיש לי פה משהו בלתי תלוי, אז...
אני לא הבנתי.
בדרך כלל בטא גדול כאילו יותר?
אז בעצם זה נכון שהממוצע של זה הוא כאילו אם הממוצע של הסכום על אלפא הוא יותר גדול, אז יכול להיות שהממוצע של אלפא פה יהיה יותר קיצוני, משהו כזה, אבל השאלה של אם זה אינדפנדנט, זה מין הסטיות משם, correlations משם, אם פה לא הממוצע עצמו, אלא הסטיות, ואם יש לי פה סטייה באיזשהו אלפא אחד מהם שהוא יותר גדול, אני יכול להגיד לאיזה כיוון זה משפיע. לעומת זה, כי זה יכול להיות חיובי, יכול להיות שלילי, אני סוכם על הרבה כאלה.
אני רוצה נראה לי כמה סטודנטים ודאי, ולקבל את הערכה כאחד והסתובב ביחד, ספרו את זה, אני מקופי אחד זה השבוע עם חג ולפני שבת וגם אפילו נמצא שבוע
גם אני הצטבטתי כל שבוע.
אני חושב שכאילו
כולם קיבלו תורה.
שכאן מאוד כן, לפעמים את החברים מקבלים לאספקט על הטיפה, אבל זה גם אספקט מי שדיברתי גם שבועות.
אוקיי.
בבקשה.
אוקיי, בסדר, נראה כמה ימים.
תודה.
אתה יכול להגיד כאילו איך לחשוב על העניין של הממוצעים, כי אני לא מבין, כאילו יש פה סטוכסטיות שנובעת מהגרלה של ה-J. נכון, זה המקור שזה ממש כזה. עכשיו, בזמן אין משהו סטוכסטי. רגע שיש לי J, אז הדינמיקה היא דטרמיניסטית. אני לא בטוח שאני מבין מה אומרים הממוצעים השונים כאן.
אז כאילו בינתיים אתה יכול לחשוב על זה כאמפירי. empirical averages. עכשיו, כמעט כל המהות של דינמיקה כאוטית זה שלמרות שזה דטרמיניסטי, בפועל אין לנו דרך להתייחס לזה חוץ ממשהו אקראי, כמשהו כן סטוכסטי. ולכן אנחנו בכל זאת,
לא, בסדר, בגלל שזה פונקציה של משתנה מקרי זה עדיין מקרי, אבל אז אני לא מבין מה ההבדל בין למצע, כאילו, כשאתה אומר אני ממצע על אוכלוסייה או למצע על הזמן, אתה ממצע בעצם על אותו, פונקציות שונות, אבל זה מין אותו ממוצע, נכון? כי זה מה שאני לא לגמרי. כאילו כשכותבים כזה
אתה אומר באופן עקרוני הרנדומנס זה על J, ואז אני כותב HI ואני אומר ממוצע, אבל
הרנדומנס הוא פונקציה של J, ולכן זה צריך למצע.
כן, אבל זה לא ש-HI, זה HI פונקציה בזמן, זה פונקציה עכשיו random variable שתלוי ב-J, כן? ויש לי הרבה כאלה. כן, יש לי בעיקרון יש לי וקטור. גם וגם, נכון, יש לי וקטור שלם על כל האוכלוסייה וגם יש לי כל הזמנים. עכשיו זה גם יהיה, בעיקרון זה תלוי על ה-initial condition. עכשיו מסתבר שזה לא...
זה נגיד שנשכח מהר.
בדיוק, זה נשכח מהר. אז יש לי וקטור שלם וגם תלות בזמן. אז עכשיו, וכל זה אקראי, אז אני יכול, בעיקרון, כל HIT זה random variable. ואז אני יכול למצח קודם כל על הזמן, אחר כך.
כן, טוב, קשה להבין את זה, אבל אני מנסה כאילו...
יש איזשהו קשר לזה שזה כמו בודי, שאתה יכול לתרום את הכל לא בזמן או באוכלוסייה,
יש קשר, אבל אז זה מין סוג של ארגודיות שונה, שאם אני חושב על זמן, אבל זה מעניין, כי זה באמת סוג של ארגודיות, שאם אני אעשה J הרבה פעמים עכשיו מחדש, זה כמו לעשות ממוצע על כל האוכלוסייה. זה כמו על כל האוכלוסייה, אז זה סוג של ארגודיות, אבל מין ארגודיות מרחבית, משהו כזה. מבחינת הזמן, אז זה לא בהכרח, כאילו, מבחינת האוכלוסייה, זה חלק מהעניין זה היה יכול להיות, ויש מערכות קצת טיפה שונות מאלה, למשל ברגע שיש E ו-I או משהו כזה, אז באמת יהיה לי נוירונים שיהיה להם time average שונה אחד מהשני. בינתיים פה זה לא קרה, וגם אפילו פה זה גם לא יקרה, כאילו כל ה-time averages בסופו של דבר, בינתיים יהיו באמת אפס, ואז היה אפשר להגיד, טוב, לא אכפת לי, יש לי HI אחד שמייצג לי את כל האוכלוסייה, רק הוא יכול להיות שונה וזה. וגם דרך, צריך לחשוב אולי כדאי להציג את זה ככה, באמת זה יכול, כי בסופו של דבר אפשר באמת להציג את זה ככה, HI טיפיקלי, אחד שמייצג את כל האוכלוסייה, כל השוק שלו, אבל איכשהו, כן. כן, זהו, בשבילי בסופו של דבר להבין את המערכות האלה הייתי צריך לעשות את החלוקה הזאת, את הענבים זה ממש באמת שאם אתה קורא במאמרים המקוריים, כאילו אין את זה, כי יש לך איזה mean field, זה dynamic mean field, וזה ניורון אחד שמייצג את כל האוכלוסייה, וכותבים עליו משוואה דיפרנציאלית, ופה זה כאילו איזה משהו גאוסי, זה הכל, כל האוכלוסייה כל האוכלוסיות, אבל אני...
כמה זה מקביל או שאני סתם מדברת עם עצמי שאני צריכה לעשות איזה אייטים כלליות של המערכת, אנטרופיה או קונצנטרציה כללית.
אז ברגע ששברנו את ה-J שהוא לא סימטרי, אז אין לנו פונקציית אנרגיה בכלל. אז יצאנו משם, כאילו, יש איזה הגבלות לספין גלאס, ששבירת סימטריה במין צורה פרקטלית במרחב, ועכשיו אנחנו גם עושים את זה בזמן, ובהיסטוריה של זה חיבור ישר, כאילו בעצם משם אפילו לחקור את המערכות האלה, אבל כן, מבחינת התכונות הפיזיקליות כמו אנרגיה וזה אין לנו בכלל, אין בכלל אנרגיה, זה לא...
כאילו, אבל הוא קרא לזה JT, זה כאילו אומר זה הממוצע, ואני לא רוצה לזכור, אבל מה שאמרתי עד עכשיו. קיצור, נראה לי בשיעור הבא, הוא פשוט יתחיל יקרא ל-JJ ויקרא לקחת. אם הוא לא יעשה את זה, אני אגיד בא לזה. זה כוח, איך הוא עשה את זה? מה התוצאה? של JJ. אז הוא אומר, JJ לא תלוי בזמן, אבל המוצא על הזמן של JJ הוא JJ עצמו. אוקיי. וה-SJ הוא דבר שמשתנה בזמן. אם הוא לוקח H בריבוע, אז קודם כל רושם H בריבוע, ואז הוא סגר על הממוצע. הוא סגר ממוצע ל-SJ בריבוע. הוא פיתח את זה או שזה עושה? הוא פיתח את זה. הנה זה פה.
זה גם זמן וגם population או רק population?
זה דומה, זה לא בדיוק אותו דבר. זה זמן ו-population.
אז זה גם זמן וגם population עושה פה עכשיו?
הוא עושה בעצם ממוצע population אחרי שהוא עשה מיצוע לזמן.
פה זה אומר... פה יש לנו
זה הגדרות, זה ממש הגדרות.
אוקיי, הנה, population. ואיך הוא כותב, איך עושים את זה או שלא?
אז פשוט אתה מפעיל את הראש. למשל, מה שקורה פה, הממוצע, נגיד JJ שווה לזה, אבל זה שווה כל הזמן ככה, נכון? אז הממוצע על הזמן נותן לך את הערך הזה. סבבה. JJ ממוצע על הזמן שווה לדבר הזה, או הזה, לא משנה. אבל הממוצע על הפופוליישן שווה לאפס. כי כאילו יהיו לך נוירונים כאלה, יצטרו חצי וכאלה יצטרו חצי. זה פשוט סימטרי.
אז בוא נראה, פה הוא עושה את זה, הוא לא המשיך את זה. פה הוא עושה population על זה.
נכון מאוד. ואז מה שקורה זה שאם אתה עושה ממוצע, ממוצע population, בדיוק מה שקורה פה זה מה שאמרנו עכשיו, נכון?
זה כאילו?
כן, הוא כאילו סגר על זה ריבוע.
כן, מה זה אומר ששווה לאפס, בגלל שזה...
בדיוק, אז הוא נותר עם האיבר הזה. ו-JJ בריבוע, population, זה בדיוק זה.
למה אתה שורש? למה זה לא בריבוע?
לא, אז יש לך n חלקי n בריבוע, אז אתה נותר עם איזשהו איבר שמסתובב בריבוע שלך.
לא, אבל ה-JT אתה יכול בריבוע.
אתה צודק, הוא שכח.
למה יש פה n? שזה התחום הזה?
קיצור קיבל איבר מ1 חלקי n, אבל זה בריבוע, אז זה לוקח שורש.
אז פה הוא ממשיך? מה זה?
לא, זה היה טבח משהו.
אז מה זה?
הוא התחיל מפה והמשיך פה.
לא, רק נראה שזה בסדר אפס.
יש הבדל, זה ריבוע של הממוצע וזה...
שזה שווה לאפס, כאילו. זה ה... זה Variance, זה פחות זה, ואז זה האיבר שתמיד מתאפס לנו. נכון, זה האיבר שתמיד מתאפס לנו.
שניהם אותו סדר גודל. קיצור, ה-Variance שלך הוא אחד חלקי זה, וה-Standard Deviation שלך הוא כזה. וואו, אני בהלם שאני הבנתי מה קרה בשביל. נראה לי. להגיד שהבנתי זה לא נכון?
anybody have any AA batteries by chance? אין שם. לא, בדיוק בדקתי את זה.
זה בריבוע? זה בריבוע?
כרגע זה שם, אני בטוח שבשיעור הבא שלא יהיה.
תדע, 3 פעמים חזקה וזה, תוריד לה.
לא, למה לא יודע? אני רק יודע שאתה
זה פרצוף של תסביע.
זה הטמפורל, זה השונות בזמן, השונות של האינפוט בזמן. אם יש משהו משתנה בכלל בזמן.
שיש פה בטריות. יש לי
יכול להיות. היה פה אחד שאני אולי... All right, let me just, in the meantime, make a few more comments on what we've done so far, which I'll have to rethink about the presentation for next year. One thing, okay, this is the temporal fluctuations in the sense that we have the momentary input squared. You can go back even a step just for the sake of it. Right, the variance in time will be hi minus time average squared.
What is this again?
This is I'm just going through them a little again more formally. The variance, the thing we did at the beginning, and outside of that, I'm taking the population average. Another way to write the variance is as the average of the square minus the square of the average. And then again, I'm taking the population averages. And I know that this part is 0. Or close to 0, 1 over n. And so I'm looking at this term, and then that's the fluctuation. That's the variance in time. Okay, now, so some questions in the break. Another way to think about this whole system is the randomness comes from Jij. And then we have a vector of inputs, hi, for all the neurons, and a function of time. It may depend on it might depend on initial conditions, but kind of ignoring that aspect, we can think about we're doing these averages first over time, and then over the population. And it could be that I could have just done the whole thing as just kind of a single randomness, looking at a single hi, and maybe skip this kind of first let's do time, then let's do space, and just set hi as a random variable that's dependent on Jij. Let's study the statistics of hi. I'll have to think about that maybe next year. If you come back, I'll be teaching it that way. But anyway, so what we found here is that this kind of conventional scaling that might have made sense to us, where each synapse is 1 over n, gives us something that doesn't change in time or in space. Doesn't have variability in space, doesn't fluctuate in time, and that motivates the fact that we're going to, in this chaotic network, we have a scaling where the variance of the synapses are 1 over n, and so that the typical single synapse is like 1 over square root n. So we're going to go through and compute at least some of the same calculations that we did here for that network. And specifically what I'm going to do, instead of studying that Jij where Jij is Gaussian, we're going to study this Jij, which is very similar to the one that we just studied, but instead of the scaling of 1 over n, we're studying the scaling of 1 over square root of n for each synapse. And I'll tell you right off the bat, it turns out that studying this network is totally identical to studying the one where Jij is Gaussian. That's how it turns out. I'll just say briefly, the reason for that is because what we're interested in is really the HI, the statistics and the dynamics of HI. And after we sum over all the Jij's, anyway, the whole thing is Gaussian. So it doesn't wind up mattering if the individual Jij's are distributed plus minus with a given probability or Gaussian. What matters is that their mean is to equate their mean and their variance, and then the overall statistics will be similar. So in this case, what we've done, Jij plus or minus j over square root of n, so of course the average Jij is 0, like in our Gaussian case, and the Jij squared on the average is just j squared over n. So that's why I choose this.
Why did we start with the Jij without the square root?
Sorry?
Why did we do that with this step if not
Without the square root?
Yeah.
So that's to motivate this issue of the scaling. So we just showed what turned out to be a non-interesting conventional scaling, which is non-interesting, and now moving to the chaotic scaling, might call it. And this might also be called, in terms of the physics of it, the spin glass scaling. Maybe. I don't know if people use that term, but okay. So now we're going to go through and study the statistics of HI. Very similarly to what we did before. That's almost identically, just we've changed the scaling. So again, we can look at the quote-unquote excitatory and inhibitory components. Triple or double? Oh, I'll try to talk loud. Maybe it'll. I don't know. On the recording, can you hear anything like outside of the? Yeah. So if I like talk really loud, maybe. Okay, so I'll try to talk loudly.
You have
If I stand here for the. I can't do it. Okay, so again, we're going to split up the input onto a neuron into the quote-unquote excitatory and quote-unquote inhibitory parts, as we did before. Calculate do the same calculation. Now this time, and this is kind of what's weird about this scaling, when we sum over approximately half of the population with a positive j over square root n, we're going to get a net sum out here that has square root of n times j and effectively the average, the half. Okay, so the net excitatory input is potentially very large and scaling in this weird way, growing with the population size. It's weird. And if we look at the inhibitory input, we'll find the same thing, but negative minus square root of n j over 2 times the average. Okay, so this is what's weird about this scaling. It gives us something, at this stage at least, it's counterintuitive. We have input onto single neurons that seem to be scaling in a bizarre way with the network size, and they're very large. What about the time average of a single neuron? what can we say about that? So last time we kind of just said, oh, well, this is plus this, and this is minus, the sum is equal to 0. But we'll have to be careful this time about the order of magnitude of the deviation from that. So again, I should still write this as approximately, because each neuron receives only approximately half of its inputs are positive and approximately half of its inputs are negative. So we'll see that in the population average, of course, we'll get 0. When we average over the whole population, the net input will be 0. We'll do this in a quicker way than we did last time. So this time we just have Jij, something over all j this time, and the average population activity. And now, it's just by taking the average over the whole population, we're going to get that the average over the whole population is 0. But what about single neurons? What about the variability in the population? Okay, so what I called before the spatial variability. So now we studied the variance. So we have single neurons input averaged over time. So we square that. And then, right, to take the variance over the population. So this gives us terms just like we saw before, where we'll have sum over j, Jij squared, Sj squared, and then that set of terms where j is not equal to k. These are going to be 0 anyway, but let's write it out. J, k. Again, the j not equal k terms are going to be 0 because of the independence of different J's. So now, back to the same term, the same looking term that we had before, but now what do we have here? We have n terms. Each one of these is j squared over n. That's the crucial part of the scaling. The variance of scales this time is n instead of n squared. And so we find that the variability across the population is order 1. And so that's the crucial thing of the scaling. Now, potentially, different neurons can have different net inputs from one another. Not everything is 0. And so even though when we broke apart excitatory and inhibitory inputs and found that those independently were very large, but in the average, everything's averaging around 0, but the variability is significant, unlike before. Before, the variability was all very small and shrinking with n. This time, the variability and the differences between individual neurons are potentially significant. They're order 1.
So this isn't 0?
So, no. So the individual one, so I should write here, it's order 1. Like here I can write out explicitly the variance of the population, j squared. And so basically one way to conclude this is to say, okay, so the time averaged input onto the neurons is going to be Gaussian over the population with mean 0 and variance j squared times this s squared. Now, I haven't yet said anything about this. I've kind of just like assumed I've left this aside. The reality is that these two pieces are related to one another. This is basically connected to the variability in the firing rates of the neurons, and the h is their inputs, variability in the inputs of the neuron. So there's a self-consistency here that's required, which we're not going to close the loop and solve these whole equations. Going back to the concept of self-consistency that came up in previous networks act in much simpler ways. This network requires very complicated self-consistency, which has to do kind of with the variances, how the variances of the firing rates drive variance in the input HI. But in terms of the statistics of the time average input, so yeah, the average is 0, but the typical one is order 1. So I can't say it's 0 here, I should say that it's order 1, and that it's drawn from a Gaussian distribution with this variance.
I'm confused. Why is it different from the result we got before and how? Because it's only in the fluctuation that 50% will be excitatory, 50% will be inhibitory.
What's different from what I did in the first hour? Just the scaling, right?
Yeah,
Just the
no,
strength.
like how, why would it affect it? Because in this term, 1 of the question mark, so it's only approximately equal to 0 because it's not exactly half, right?
Yeah. Right, exactly. So it's like this approximate term where I said this is approximately half of the population. It's approximately up to an order of 1 over square root of n. An order 1 over square root of n synapses for any given neuron are kind of on the wrong side, are additionally positive or additionally negative, and essentially that gives us the order 1 result. It's kind of like how, right, if we look at this is the identical term that we saw before, a sum over which JIJs are positive. How many JIJs are positive? We said it's close to a half. But how close is it to a half? Is a half plus or minus something that's 1 over square root of n?
Why plus n? Because it didn't change probability.
Right. I mean, I don't want to calculate, we can leave it as an exercise just to calculate the randomness on that level of how many are positive and how many are negative. The difference is that last time we ignored it. That's really the difference. But, I mean, we didn't ignore it. It came from this calculation. Right here, we effectively calculated the variance. We found last time the variance was 1 over n. So that was something that we could ignore. We had a mean we had a mean over the whole population that was 0, identical to this, and then we had a variance that was 1 over n. So we said, okay, there still might be some variability, but it's very small. And this time when we did the calculation of the variance, and we could do it in about, I'll leave it to you aside, we could do it from the perspective of how many are positive and how many are negative. We find that the net effect of that is order 1. So I want to go on.
Zoom out and put this in context. I mean,
Yeah.
like what you're doing, like what we're doing.
Yeah. So let me get to just write out the temporal, the result of the temporal variability, and then come back to the mean, because that's kind of the interesting thing, the most interesting thing. So they're both interesting. The most interesting thing is the temporal variability, which is effectively random, that arises in the system. We have this emergent chaos in the network. The network itself is fully deterministic. But because of the randomness in the JIJ, it turns out that the dynamics in time are effectively random. And that relates to the temporal fluctuation. But it is also of interest that there's a spatial variability as well. Where each neuron is potentially very different from its neighbor. Even though their statistics are identical, we drew them from the same distribution and everything about them is identical, but we have this kind of breaking of that symmetry, both in the space and also in the time. So write out the temporal fluctuations. Again, maybe this whole presentation is a little bit silly. We should have just jumped straight to this and ignored the aspect of the time and the space. Because effectively the calculation here is going to be almost identical. Right? This time the variance in time of the input to a single neuron. So we have those two terms, Gij squared, Sj squared, which is the variance in time of the activity, plus the term j not equal to k, jij, jik, that's jik. Again, when we take the population average, the second term will fall, and we'll be left with the same thing that we have here. Which is just j times these fluctuations in the activity. So, in particular, it's order 1, right? So what we find is that, right? What is this term? This is effectively the variance in the firing rates of the neurons. So if the neurons have some kind of temporal fluctuations, they will drive fluctuations in the input of the neuron. And this is different from the previous scaling. In the previous scaling, even if we had somehow we were like momentarily driving fluctuations in the firing rates, they would yield fluctuations in the input that was just order 1 over n. So they would die out. I mean, if we have fluctuations in the previous scaling, they would just die out, dissipate across the network very quickly. Everything would come back to 0. But in this case, we have this possibility of this kind of self-propagating loop of fluctuations, and that's what winds up actually happening in this network. Where on the one hand, if neurons fire with some kind of fluctuations in time, the firing rates change. That then drives order 1 fluctuations in all the neurons' inputs, and then that's a loop.
Is it balanced in some way? Or just get what?
It's an interesting question. Is it balanced in some way? Kind of. What do you mean? Like it?
If I think about neurons, it doesn't sound like a good idea to excite.
Right. So, at least in this model, right, the actual activity is bounded by the definition of how we have tangent hyperbolic. So the whole thing is within the range of -1 to 1 in this model. So it's a propagating loop, but it's not a divergent. It's not a loop that can diverge and just explode. It's a right, and in a sense, kind of when you ask about balance, it makes me want to talk about the mean. So in a sense, and we'll get to what's called the balanced state network somewhere down the line, which is very related to this, where there we do have more biological neurons in E and I. And the key is really that the mean is balanced. So here the mean is always around 0. So nothing can explode and diverge and go crazy overall, because the mean is always going to be 0. So that kind of self-propagating loop is this bizarre one where it's propagating fluctuations. Fluctuations around 0 are just self-propagating within the network. Any question?
Quantitative 1. Is this J the same J here? That's a G?
Yeah, so here we can think about it as exactly the same, because we found that this Jij gives us a mean 0 and mean squared j squared over n, which is exactly the way we defined it in the beginning.
The fluctuations are propagated, but it seems like they're being amplified, right? It seems like eventually the network gets saturated from being.
So that's a very delicate question of how we actually close this loop. The size of these fluctuations drive these, but then the question is on the other side, how are these derived from some kind of function of the fluctuations of the input? And that's not trivial at all. Last year I tried to do it in class. I don't know if there was any benefit to having done it. People can testify. Maybe there was, maybe there wasn't. But and I'm happy to do it as some kind of bonus because it's fun. But yeah, it turns out that there's And this is really where the self-consistency in this model is required. You have to close this loop where these fluctuations will lead to these fluctuations, but then how do you go about closing that and so that there is a self-consistent solution to that set of equations.
Can you explain again why the order 1/n fluctuations will die out and the order 1/n?
Yeah, so previously, with the other scaling, we had hs squared was, if we wrote it out fully, j tilde over n times s squared. So s squared is the side of the firing, and then h is the side of the input. So in this case, if I kind of artificially make the neurons firing fluctuate momentarily, anyway, the fluctuations in the input to any given neuron they're effectively washed out with the 1/n. So the fluctuations in the input are very small. Even if this is significantly fluctuating, fluctuations in the input are very small. And if fluctuations in the input are very small, the resulting fluctuations in the output would necessarily also be small. So that's the sense in which they'll die out. That makes sense? So it's really like from this term that we calculated before, where there's a 1/n factor.
Might be a very big distinction, just because before you use the fact that it's not exactly half, but then here you use the fact that you average over the population and you say it's 0, but it seems to be inconsistent.
And those are the subtle things. When we average over the whole population, then it becomes exact. So over here also, if I average over the whole population, then this will become exact. So here, if I average over the population, this becomes exact. Square root n j times the mean, minus square root n j over 2 times the mean, and then the average is exactly zero over the population. Here, so here also, when I take the population average, then I have consider exact.
But it only gives you 0 because it's exactly the same number.
This?
Yeah. Because the average of j I
The average of j
is 0
is 0.
only if exactly, yeah, but only if exactly half and half.
Here I'm doing it for the entire. Here I'm calculating for the whole input.
Maybe I would have said it.
Okay. Yeah. Here I'm doing it for the entire input, both the positives and the negatives all in together. Okay. One more comment about this transition. So if we go back to our dynamic equation, f dot I is minus si plus tangent hyperbolic hi. And now we said effectively hi is Gaussian. And I said before that it's Gaussian in space, with differences between neurons. It's also, from what we find here, it's Gaussian in time. It turns out to be a Gaussian process, which I'm not going to introduce the formalism of what that is, a Gaussian process, but it's effectively a random variable that's changing in time. Every time point is a Gaussian random variable. And so kind of from this equation, the requirement to find self-consistency comes from having to basically effectively solve this equation and solve for this particular statistics of s that we're interested in, which is this guy. And so that I'm not going to do, but sort of maybe you can get some kind of intuition that it's even possible. This equation as a formal equation, I know how to solve. I have a linear differential equation and then some kind of fluctuating input. So I can do an integral over all past times and e to the t minus t prime tangent h I of t prime over the past input dt prime, and kind of at least formally write the solution to the firing activity as a function of the past fluctuating input. Now from here I'd have to actually calculate the statistics of this, and that's what becomes becomes complicated, but it can be done. And yeah, so that loop can be closed, and there's this kind of self-consistent fluctuations that that propagate in a steady way through this network. And I would like to show simulations of that. Any questions?
Do you think that neurons are chaotic?
Yeah, I do. There's a lot of interest in that question, whether neurons are actually chaotic. And when we'll get to more discussion of it in the context of the balance of excitation inhibition balance. But one of the primary observations of neural firing in the cortex in particular is that the spike times of single neurons look like they're random. They appear to come from a Poisson process. We'll discuss that more in the future, but if you look at a single neuron spike times, it's hard to make any sense of the pattern of spiking. And also the correlations between neighboring neurons in their spike times are relatively small on the average. And those kinds of observations lead people to think that at least the cortex might be a chaotic system.
Time extension, or talking about also both?
Both. Both.
But if you do see more spiking activity because you introduce the stimuli.
Right, so there's an elevated level, but in terms of the particular timings, those to my knowledge are always appear random-like. But we'll get to that in the future. It relates very closely to this model, but it's extended to models of neurons with excitatory and inhibitory neurons, and with spiking.
So you're saying that rate has meaning, but the component is
That's what is often. I mean, that's a major debate. A major debate is whether spike timing has meaning. The observations in the cortex of spike timing that kind of just looks like it's like a Poisson random process led people to think that the only important aspect of it is rate, that only coding in the cortex must be rate based, and that maybe the underlying spiking is chaotic. It's definitely still open question. These are all what I want to show you, but I'd like to actually run it from scratch. Okay. Okay, so I'm just going to run a straightforward simulation of the system as we defined it here. So here I called it R for some reason instead of S. We have a set beta equals to 1 in accordance to what we discussed. I put the entire beta times G parameter into the standard deviation of the Gaussian. So here I'm running it in the Gaussian form of Jij, not the Jij equals plus or minus. Again, those wind up to be statistically equivalent. Okay, so that's the dynamics. Okay, and now I'm taking just 4 random neurons and show you what their activity looks like in time, together with the population average. Oops. So that's what it looks like. The average is in this dark black. It has these fluctuations, but it's very small. It's close to 0 on the average over time, but it changes from 0 at specific times. And then these individual neurons have these total random like fluctuations. They're just going wild. Of course, if we go to a j which is less than 1, we should observe what we expect to observe is that the 0 fixed point is a stable fixed point. And though we might start with some random initial conditions, and we might have some initial fluctuations, we'll very quickly fall to that 0 fixed point. So that's what we see here. Here the condition was that this j here, or beta j, what we call beta g before, is less than 1. Right? What we showed last time, beta g is less than 1, then the 0 fixed point is stable. That's what we see. Now I'm taking 3 random neurons and just plotting their activity, the activity trajectory in space relative to those 3 neurons. So that's what it looks like. Neuron 1 along the x-axis, neuron 2 along the y-axis, neuron 3 along the z-axis. And we just have chaotic activity. And in contrast to the Lorentz chaos, which only had 3 elements to begin with and had this beautiful butterfly kind of emerge from it, we're not going to see any butterfly here. We're just going to see apparent randomness.
Maybe there's like a tighter butterfly.
I mean, maybe if we go into higher dimensions. The truth is, maybe like for small. Yeah, I mean, there's all kinds of things to ask about this question in terms of like in the field of like studying chaotic dynamics. Like, what is the dimension? We talked a little bit in rough terms about the dimension of the attractor. So in the Lorentz system, we saw the whole dynamics converge to this butterfly thing, which was almost like a single surface. So it was like some dimension a little bit larger than 2. So there is some dimension to this chaotic attractor. I don't know what it is. I think that it scales with n, though. I think. But that means that there is some kind of low-dimensional structure in principle to be found, and maybe for example for small j, where j is very close to 1, certainly for finite n, there might be something a hyper butterfly out there. I don't know. Okay, now another aspect. One of the parts of the definition of chaos that I mentioned. Is the sensitivity to initial conditions, and I showed it with the Lorentz attractor. So here I just want to also we'll simulate another trajectory where we start the initial condition very close to the one that we already simulated, and see how it progresses in time. So at the beginning they're together, but very quickly the 2 trajectories diverge from each other, and they continue on and are eventually totally forgotten. So at some point later on down the line, the system has no idea that it started really effectively at the same place. Any observer looking at it would have no way at all to tell that these systems were initialized really close to the same sense. In that sense, memory in this system is forgotten very quickly. We can start the system in one place and hope to, at a later time, be able to read out or decode where it was started, what was the initial condition, and we won't be able to. And in that sense, there's kind of something disappointing about the system. And functionally speaking, it has this limitation that it's no good for memory. Everything's forgotten very quickly. It turns out that the interest in these kinds of systems then is not at all for their memory, but for the richness of the dynamics. And there's been a lot of work in the last decade studying how these systems can be used as a tool to learn complex tasks. So people have used these as a kind of a black box where you start out with a system which has these bizarre and chaotic, random-like complex dynamics, and you want to drive that system to do some kind of task. And I can put up on the Moodle some examples of these articles that have done it. You want it to perform some kind of input-output relationship that has a complex dynamics to it, that has a time dependency to it. So not like Hopfield input-output relationships where we kind of have, okay, a memory pattern should give us the memory pattern in this static sense, but if you want a system that can do maybe a kind of a motion where given some kind of input, it'll make some kind of smooth motion in a given output, so then this kind of chaotic system can be a powerful resource, to put it vaguely. You kind of have this black box initially doing a random thing, and so that you can train it, you can entrain it to do complex dynamics that you want it to do. So that's one of the particular interests of these systems, and yeah, really like the last 5 years I've seen a ton of work on this. Larry Abbott, who's coming to the conference this week, has done a lot of that, and that might be what he's talking about when he's here. And it's also been used, kind of funny way as a modeling tool to model neural activity. So given a set of neural activity, people have trained these kinds of networks and then studied the kind of resulting solution that this network comes to and compared it to neural data, and then at least in some cases found that the resulting solution that kind of emerges from these kinds of networks reflects certain properties of the actual neural data.
Can you pull out some variable that is as informative as rate, for example, from this information?
As rate?
Something that you can do,
yeah.
That a different is
right. So you can do it in a number of different ways. You can kind of, but you can take a readout vector of the whole population activity. Instead of just the average, you can kind of project it onto a certain vector, and then you can require, or you can train the network so that particular readout does what you want it to do. So okay, that's it for now. So again, there's no class on Thursday. I think now let's see. Plan was to talk about Lyapunov exponents and the sensitivity of initial conditions in the system. So that may or may not be what we do next week.